So it's the 5 points.
The extra credit? Yeah.
Apparently there's like a 7-point curve. Curve is 7 points. 7%? What is it? 7 Harry Potter movies. No, there's 8 Harry Potter movies, 7 Harry Potter books, 7 Horcruxes, 8 parts of Voldemort's soul.
All right. So we're going to continue for what we were working on last time, which was glycogen phosphorylase. So this is the chapter 15 part of the notes where we talk about enzyme, how to regulate enzyme activity. The last couple SI sessions we went through, I'm not going to go over in detail. We went through covalent modification, which is the first thing that was taught to you guys with how enzyme activity is regulated. Zymogen activation is another one. Of which there are 3 examples given in your notes. Isozymes is another way to regulate enzyme activity. Feedback inhibition is as well, and we're going to do some practice with metabolic pathways today. And then we talk about allosteric enzymes. Yeah, I don't know if there's going to be room on there. And then we talk about allosteric enzymes and how they're uniquely regulated compared to Michaelis-Menten enzymes. As a reminder, the thing with allosteric enzymes that's unique about them is that there are 2 forms that allosteric enzymes take. An inactive form that you see on the left here, and an active form that you see on the right. There is always a population of both of these for an allosteric enzyme, and depending on conditions in the cell, the enzyme will shift into an active state, or the enzymes will shift into an active state or an inactive state. We talked about what effectors shift enzymes into either an active or inactive state, and that's a simplified version of what this picture tells you. Activators and substrate molecules shift allosteric enzymes into an active state. Meanwhile, inhibitors shift enzymes into an inactive state. It makes sense. Inhibitors want to turn off the enzyme, so they'll cause the enzyme to shift into an inactive state. Then we start to talk about glycogen phosphorylase. One of your possible extra credit questions, this time you won't, unless he does something different this semester, this time you will not be told exactly what the extra credit question is going to be. It'll be one of 3 possibilities. This is one of your possible extra credit questions, is to explain what glycogen phosphorylase does and specifically how it is regulated, which we will cover right now. I started covering it a little bit on Wednesday, but I'm going to start over with it, and you'll see how it's regulated. So, what glycogen phosphorylase does is, well, since he's talked about chapter 7 some already, you guys know what glycogen is, right? What type of biomolecule is glycogen? Is it a protein? No. What is it? Polysaccharide. Glycogen is a polysaccharide made of a bunch of what monosaccharide? Glucose. So glycogen is made of a bunch of glucose molecules. It is a compact form of glucose, is what you can think of it. And so if the body wants to use that glucose that is a component of glycogen, the body has to break down glycogen into glucose. The very first enzyme that begins that breakdown of glycogen into glucose is the enzyme glycogen phosphorylase. So its job is to start that process of breaking down glycogen into glucose. All glycogen phosphorylase does, its only job, is to phosphorylate glucose. In fact, I think that is what this picture is here somewhere. Here's glycogen, and it phosphorylates it, okay? The rest of this process you'll learn in Biochem 2, or if you're studying for the MCAT, you will have to study the mechanism. But for now, we only care about how the enzyme itself is regulated. It's a very unique enzyme because it is regulated 2 ways, and the result of that is that there are 4 possible combinations that this enzyme can take. And this time I'm going to draw it out, and then we'll come back to the picture in a second. Okay, so hopefully this comes out. All right. So glycogen phosphorylase. All right. So like I said, it is regulated 2 different ways, and I'm going to simplify the diagram even more than what was on the in the notes there. I'm going to start with this. Okay, I'm going to fill in some stuff and then we'll explain it. Okay, so I'll begin with the top part of this diagram. So glycogen phosphorylase is regulated two different ways. The horizontal part of this diagram is describing how this enzyme is regulated via covalent modification, which is the simpler one to understand, because all covalent modification means is that you're covalently attaching or removing something from this enzyme. In this example, there is an enzyme that covalently attaches phosphate to glycogen phosphorylase. So each of these circles, by the way, represents glycogen phosphorylase. If you don't remember what T or R stands for, I'll go over that again in a little bit. But each circle represents one of the four possible states glycogen phosphorylase can be in. So we're only looking at the top half right now, and it's describing covalent modification, where we're covalently attaching a phosphate to it. What enzyme will attach a phosphate to this thing? What is it called? Yeah, or kinase, exactly. Something kinase. I don't care what the exact name is, and you don't have to give me the exact name if this happens to be your extra credit question. I don't know which one it is yet, because he hasn't chosen, but in the past, I'm fine with people just telling me that that's a kinase, is the one that attaches a phosphate to glycogen phosphorylase. What's the one, therefore, that removes the phosphate? Phosphatase, exactly. Something phosphatase, it removes it. Each of these enzymes, the ones that are doing the modifications, are called converter enzymes. The ones doing the modifications are called converter enzymes. So both kinase and phosphatase are converter enzymes. What term would you use to describe the enzyme being modified? Interconvertible is exactly right. So the one being modified, which in this case is glycogen phosphorylase, is the interconvertible enzyme. The one being modified. Okay. We'll see after we finish filling in everything what the effects are of covalently attaching a phosphate to this enzyme are. It is a pretty extreme effect. But for now, that's it for the covalent modification portion of this diagram. The vertical portion of this diagram, if you look in the picture, they label it as non-covalent regulation, which is a synonym in this context for allosteric regulation. You can put either one, non-covalent regulation or allosteric regulation, either one is fine. So we learned about allosteric enzymes. The key thing with allosteric enzymes is there are two possible states they can be in. T for tense and R for relaxed. The tense state is the inactive form of the enzyme. Okay. And that's true for both of these up here. And R, which stands for relaxed, is the active form of the enzyme. Okay. So only when glycogen phosphorylase is in either of these two states will it be able to perform its function. Up here, it's not able to do anything. So there are certain molecules, which we call effectors, that will shift glycogen phosphorylase more to either the active side or the inactive side. We call those effectors. The one molecule that pushes it towards active is AMP. And I will give one example and more later. One example that that shifts equilibrium towards the inactive side is ATP. Here's a quick way to internalize why that is. So what is glycogen phosphorylase's purpose? What is it starting? What pathway is it starting? What is it controlling? The breakdown of what? Glycogen, right? The point of glycogen phosphorylase is to start the mechanism of breaking down glycogen into glucose. Why would a cell want to do that? It wants to do that when it needs energy. When a cell needs energy, it needs glucose, so it's going to try to break down glycogen. Therefore, AMP is what you can think of as a representation for a cell that does not have a lot of energy, right? ATP is a lot of energy. AMP means that it's low in energy. So no wonder that AMP, if there's a lot of AMP floating around in the cell, it's telling glycogen phosphorylase we need to start making more energy, begin breaking down glycogen. So AMP causes a shift in equilibrium here to more active state. It's going to make glycogen phosphorylase more active because you need to start breaking down glycogen into glucose because there's not a lot of energy around. The opposite, therefore, is ATP. Why would ATP inhibit this thing? Well, ATP is a way for the cell to communicate to this enzyme that there's already plenty of energy. We don't need to keep breaking down glycogen anymore. We already got plenty of ATP. So ATP, no wonder, is going to cause a shift back to the inactive state. It's telling glycogen phosphorylase we don't need to break down any more glycogen, so that's why equilibrium shifts to the inactive state. There's a couple other molecules that go here, such as glucose and glucose 6-phosphate. Both of these make sense too, right? If there's already plenty of glucose floating around in the cell, why would you need to break down glycogen into more glucose, right? And glucose 6-phosphate is just the first step in glycolysis. It's basically the same type of communication going on here. Either one of these is telling glycogen phosphorylase, we already have plenty of glucose, please stop breaking down glycogen into glucose. So that's why they're telling glycogen phosphorylase to become inactive. There's one more extra molecule here, and that is caffeine. Caffeine is sometimes referred to as an appetite suppressant. And in this context, caffeine does a lot of things in terms of metabolism, but in this context, caffeine also shifts equilibrium to the inactive state for glycogen phosphorylase. So that's it for the left side here. These are your effector molecules. Each one affects glycogen phosphorylase as drawn here. AMP boosts it, everything else here decreases it. Over here on the right, we have a weird situation going on over here. It turns out, and they don't really illustrate this too well in the picture, but it turns out that when you covalently attach a phosphate to glycogen phosphorylase, and I might be using a slightly different term, it superactivates it. It superactivates it. So imagine there's a really big arrow here and a really tiny arrow pointing the other direction. So through covalent modification of glycogen phosphorylase, it superactivates it to the point that it doesn't actually need any effectors to shift into the active form. It's just going to prefer the active form after it is covalently modified. Okay, so this is a special version. Over on the right half of this diagram is a special version of glycogen phosphorylase that is superactivated. Or hyperactivated. I don't know exactly what word is used in the notes, but they usually say that this version of glycogen phosphorylase is only used for emergencies, the fight or flight response, right? Those types of things. It's usually activated when you need as much glucose in as short of amount of time as possible, and so it's only for emergency release of glucose from glycogen. The one on the left here, the term they use to describe this one over here, which is a lot slower, is it's for homeostasis, which is normal breakdown of glycogen into glucose, where you break down glycogen only when your body kind of needs it. Like if you're a little hungry, it's going to start breaking down glycogen. Over here on the right, we're talking about emergency, fight or flight response, whatever it is. It's going to be over here on the right side. It's going to the system is going to be covalently modified, and it's going to be superactivated. I think the stuff on the right here, I'll have to look. I always forget this. I believe it's ATP and caffeine at least. Let me flip back so I don't give you the wrong information. It's glucose and caffeine, excuse me. So let me fix my diagram here. So there are still some effector molecules over here that will inactivate this enzyme, and that is just glucose and caffeine over here. But they'll do the same thing that they did on the left half of this diagram. They will shift equilibrium into an inactive state. Let's see, so homeostasis, emergency, flight or fight, superactivated, blah, blah, blah. Okay, oh, and there's one more thing to add on here, and I always forget this, is the one on the left is called glycogen phosphorylase B. These two over here on the left is glycogen phosphorylase B. And the ones on the right are glycogen phosphorylase A, like lowercase a. All right, that's about it. Everything else that I've drawn on there is the most important stuff that you need to know about glycogen phosphorylase. All right. Again, the thing that I don't think this diagram does a good job of illustrating is the fact that when you are covalently modifying glycogen phosphorylase, it actually greatly prefers this state in the bottom right here. Greatly prefers to be superactivated rather than inactive. Okay.
Can you say that one more time?
The very last part? Yeah. So again, the thing that this illustration doesn't do a good job of is really emphasizing that when you covalently modify glycogen phosphorylase, and as you can see here, when you attach phosphates to it, it actually means that the enzyme ends up really preferring the active state of glycogen phosphorylase rather than the inactive state. So what I usually do when I draw this from scratch is I try to draw the down arrow right here really bold, and this one really thin to illustrate the difference. Is that when it's covalently modified, it greatly prefers this state down here rather than the inactive state. In contrast with the stuff over here on the left, which there's a nice balanced equilibrium between these two things on the left. It's very slow. It's like, all right, if we need to use glycogen phosphorylase, we'll use it for a little bit. It's very slow over here. So these arrows are drawn with equal length. Over here on the right, I would modify my diagram if I'm studying this stuff, indicate that this is a really bold line, and that one's a really small line to indicate the difference on the right half of the diagram. Yes?
So it's not as much to do with Le Chatelier's principle?
Yes, exactly. The Le Chatelier's principle is more this stuff on the left. On the right, there's a little bit, of course, glucose and caffeine do try to push equilibrium back, do try to shift it back in the inactive state, but this extra phosphate on here is just super activated it.
So it's almost like the active form is more just stable, or?
Yes, it does seem to be greatly preferred if we're talking about the right half of the diagram here.
Okay.
Okay. So this is almost everything you need to give me if this ends up being the extra credit question. So I do expect a drawing and bullet point explanation. You don't need to give me long paragraphs or anything, although I do appreciate those that did for this last extra credit. I can actually tell which one of you really studied this last extra credit, and there were those that I'm kind of sure probably cheated when they were standing in line, but I can't prove that, so they still got points. But those that showed that they knew what they were talking about is very easy to tell. So this next one won't be as easy, in my opinion, as the amino acid sequencing one. I'm going to need a drawing, I'm going to need an explanation. Just give me enough information. You can even miss a little bit of information. I don't need everything because I don't expect a whole lecture on the extra credit, but give me enough to convince me that you deserve full credit on the extra credit, if this happens to be the extra credit this time.
With enough time.
Yeah. People have done it.
Like steps and paragraphs.
People have done it in previous semesters. It is possible. So there's a little bit of information to add on here, and that is the types of effector molecules that you have. So we've written them down, but what are they? Okay. So in last SI session, we talked about phrases like positive versus negative effectors. And we also talked about homotropic, versus heterotropic. Is it still recording? Okay. Anyone remember what a positive effector does? Exactly. It activates the enzyme. A positive effector is any effector that ends up more activating the enzyme, shifts equilibrium towards the active state. Meanwhile, negative effector is going to shift it towards the inactive state. So the only example of a positive effector we have in our entire diagram is AMP. So AMP is a positive effector. We have plenty of negative effectors, ATP, glucose, yep, glucose 6-phosphate, and one more, caffeine, exactly. Okay. And that's all the positive and negative effectors. What happens if we use the phrases homotropic and heterotropic? What does homotropic mean when they describe an effector molecule?
It binds to the S site.
Yes, the homotropic means it binds to the active site, which is where the substrate wants to go to. Out of this entire diagram, you're going to get only two things that actually bind to the active site rather than an allosteric site. And I'll explain why. They are glucose and glucose 6-phosphate. It turns out these actually bind to the active site in order to inactivate glycogen phosphorylase. The reason why is that glucose and glucose 6-phosphate look very similar to the substrate of this enzyme. The substrate of this enzyme is glycogen. What is glycogen made of?
Glucose.
A bunch of glucoses. So no wonder glucose and glucose 6-phosphate can bind to the active site. They look very similar to one end of glycogen. So that's why they are homotropic. They bind to the active site. AMP, ATP, and caffeine, therefore, are heterotropic, meaning they bind to not active site, to the allosteric site. Okay. So, if we want to fully describe AMP, we can simply say that AMP is a positive heterotropic effector. ATP is negative heterotropic. Glucose is negative homotropic. You can do whatever combination here. You can draw out this table. I don't care. Just show me that you knew ahead of time what each molecule was. You don't even have to describe it. Just show me that you knew, because this stuff. A lot of people don't grasp when they talk about glycogen phosphorylase. These are where the molecules bind to, is described here, and these are how the molecules affect glycogen phosphorylase, whether activating them or deactivating them. All right, let me check to see real quick if I've forgotten anything. Let's see. Yep, normal homeostasis, emergency release, caffeine inhibits it, blah, blah, blah. There's this nice bonus fact here. I don't need this for the extra credit, but if it shows up as a multiple choice question, remember that it states here that caffeine, there's a correlation between caffeine consumption and reduced incidence of type 2 diabetes. Yes, question?
Is that because caffeine is a negative heterotropic inhibitor, so it stops glycogen from being broken down to glucose?
Into glucose, exactly. And that's right? What is one link with type 2 diabetes is increased blood sugar, right? A lot more glucose in the blood and in your cells. Well, if caffeine is inhibiting the breakdown of glycogen into glucose, no wonder that there's a correlation between caffeine consumption and reduced incidence of type 2 diabetes. Of course, though, you add some sugar to your coffee, and then that ruins the whole thing. But I can't say anything. I add 3 sugars to my coffee, so this is a nice little bonus fact. You don't need that for the extra credit, but if it shows up as a multiple choice answer or question, you now know why it is potentially why caffeine is linked to reduce incidence. Okay. Any questions on glycogen phosphorylase? I hope that was a simplified version of the mechanism. Okay. No. Yeah, there's a lot of stuff on here that if it shows up on the exam, I'll go over it at the exam review. But because they don't show up every semester, I just skip over it if I'm lecturing on it. So I'm not going to bother here. This is just an illustration of 2 other effectors that regulate glycogen phosphorylase. I never remember what, something about norepinephrine or epinephrine. I don't know. I'm going to skip it for now. because I don't care. And again, I do promise that if it's going to be on this exam, I don't know yet because it's not done being made, I will cover it at the exam review. So, these are the most important things when talking about enzyme activity, regulation of enzyme activity. So, let me pull up the worksheet, and I'm sure I've forgotten some other stuff, so let's see. Okay. Oh yeah, I haven't gotten an official room reservation yet for the exam review, but it looks like it will be a bigger room. It will be different time though. It'll be next Wednesday from 6:30 to 8:30 p.m. Okay, and it should be reserved unless in the last hour someone else stole the room. But it will be, when I get the official confirmation, it'll be next Wednesday, 6:30 to 8:30 p.m. I don't know the room yet. I will let you know when it is officially reserved. And it should be a much, much bigger room than last time. It should hold almost 300 people. Okay, so let's see. We did that, we did that. All right. All right, let's review a couple things and make sure it's still recording. All right. So this is, of course, a modified version of covalent modification with a couple things removed here. Ignore the catalytically blank form and catalytically blank form because it's not 100% true like this. But simply, all you need to tell me is what word should go here. What enzyme is attaching a phosphate? It is kinase, and the one down here is phosphatase. Where does it get the phosphate from, though? What molecule actually is able to give the phosphate? It is ATP. So what this diagram is telling you is that there's an enzyme called kinase that takes a phosphate from ATP. I'm not going to be able to type it in here. That takes a molecule from ATP and sticks it onto the enzyme. And what's left behind from ATP is ADP. It has removed one of your triphosphates. It is now a diphosphate. Okay. Most enzymes are activated through covalent modification, but because that's not 100% true, ignore these blanks down here. That's old information. Okay. 3 examples or processes that are regulated by zymogen activation. Anyone give me any one of them, one of the mechanisms? Yes.
Like insulin?
Insulin, exactly. Insulin is activated via zymogen activation. It's initially called proinsulin. It is activated via zymogen activation. Yes.
Blood clotting?
Blood clotting is another one. In fact, it's several rounds of cleaving of zymogen activation to superactivate it. And what's the third one? Chymotrypsin/trypsin, it turns out, is an enzyme that's regulated via zymogen activation. Exactly. All right. Lactate dehydrogenase is a special enzyme, special category enzyme called what? Yes.
Isomerase?
Isozyme is a bit right, but it's about right. Yeah. Isozyme or isomerase is fine. It's basically a special word that says there are several forms that lactate dehydrogenase can have. I believe it's 5 different forms. Don't worry about how many of alphas or beta subunits there are in it. Don't worry about that. What you should worry about is, oh yes, do you have a question?
What was the name of it?
This one is isozyme. It's a category of enzymes called an isozyme. Yeah, so what functions does it have? It really only catalyzes one reaction, but potentially in 2 different directions. It catalyzes this reaction by converting pyruvate into what? Lactate or lactic acid, exactly. Or it can do it the other way around. It can take lactate, it can convert it back into pyruvate. The reason why it's able to do both of these, and it depends on which, is because it depends on which version of lactate dehydrogenase you have. To illustrate this, you can review, which one is it? This slide, where you can see the exact same enzyme, just it's made of different amounts of certain subunits. And because of that, it's going to be found in different tissues doing different things. For example, if the version of lactate dehydrogenase in the heart is going to be converting lactate into pyruvate. The version of lactate dehydrogenase in muscle and liver is going to go the other way around. It's going to convert pyruvate into lactate. Okay, but don't worry about A2, B2, whatever. No, don't worry about that. Just general. What does lactate dehydrogenase do? It catalyzes one of two possible directions in this reaction here, and that it is an isozyme. Oh wait, back to the worksheet. Let's see. So don't worry about that. That's old information. All right, now metabolic pathway, and it's hard to draw this stuff, but let's take a look here. And there's almost guaranteed a version of a metabolic pathway question that's going to look very similar to this. It may ask a different question regarding it. Well, you'll probably get something that looks similar to this. So what this diagram is saying is there is a starting from the left, the beginning, there's a substrate Z. It is catalyzed by enzyme 6, because I wrote this out of order, and it turns into product A. It turns out that product A is a substrate of enzyme 1, which then catalyzes its reaction to convert into product B. Interestingly enough, though, this product, or substrate B, is a substrate of two different enzymes, enzyme 2 and enzyme 4. Half of the time it'll go up to enzyme 2 and then goes down the top pathway here. The other half of the time it'll go down to enzyme 4 and goes down the bottom pathway here. So this is the metabolic pathway illustrated for this question. What could they ask? So here's a couple potential questions. So here's the first one here. We are told, let me make sure this is still recording. All right. We are told that product G actually inhibits enzyme 2 by binding to its allosteric site. This is an example of feedback. When product G is produced, what will happen to the concentrations of product A, B, C, basically everything else? What happens to everything else if product G is produced and inhibits enzyme 2? For each one of these products states whether the concentration increases, decreases, or stay the same. So let's figure this out from easiest to hardest thing to figure out. If product G inhibits enzyme 2 and shuts it off, what can you guarantee will happen to product C? It should decrease, right? Exactly, because if enzyme 2 is shut off, well, you can't make any more of this. Then what can you guarantee about product D? Also goes down. By the way, some answers for this style of question could ask it in a way of what happens to the activity of enzyme 2? Well, if enzyme 2 is shut down, the activity also decreases. If the activity of enzyme 3 also decreases. So keep an open mind about this if the question or answers are phrased that way. But basically everything in the top half here gets shut down because enzyme 2 is shut off. Well, if enzyme 2 is shut off, B no longer has to be evenly split between the top half and the bottom half. Now B is all going to flood down to the bottom half. What do you predict is going to happen to this substrate or product here? It should increase, right? Because before, with both of these pathways open, it was kind of like evenly split, 50-50. But now that the top half is shut off, I believe sometimes Dr. Hayes gives an analogy, is that imagine this is a river that splits off into two streams. If you shut off one stream, all the water is going to flow down to the bottom one, and therefore you're going to have a lot more water down here. And in this example, it would be a lot more product down here. So F should increase, and G should increase. So this is a unique example of positive feedback. G is inhibiting enzyme 2, which causes an increase in F, and an increase in G. So this is an example of positive feedback. All right. So again, G inhibits enzyme 2, shuts off the top half, therefore everything in the bottom half increases. Yes?
Do you think you're going to fix the labeling? Because if you did, then E2 would be where E1 is, and then...
whatever label is on there, so don't worry about it. It could have been completely different letters and numbers, so... But as long as you can follow, in general, like, oh, G inhibits this, what happens to everything, you'll be fine.
Okay. So the number doesn't matter, like E1 doesn't matter, like
Yeah, no, it's just whatever label he gives you there. It could be like MNOP or whatever. It's just, as long as you pay attention to the diagram, you can make your own conclusions off of it. Now, interestingly, and this thing sometimes trips people up, what would happen to the amount of A, Z, and B though? Like, would anything even change? The answer is nothing would change. And the reason why is, well, although the top half has been shut off, everything before that step is still normal. So for all enzyme 6 or enzyme 1 nodes, everything is still going on normally. So it's going to produce the same amount of A as normal. It's going to produce the same amount of B as normal. It's only once it gets to this branch here is everything going to change. Yes?
Would enzyme 4's activity increase?
Increases.
Because there's going to be a higher concentration of B being sent to it?
Yep, exactly. The activities of enzyme 4 and 5 are going to increase. In fact, we know this, right? With Michaelis-Menten enzymes, if you increase the substrate concentration, it increases the rate of the reaction. So it will increase the activities of enzyme 4 and 5 simply because there is more substrate available to it. All right, so a summary. C and D are going to go down because enzyme 2 is shut off. F and G are going to go up because all the substrate is being funneled down to the bottom pathway here. Everything else is going to remain the same because it doesn't know that anything's changed. Enzyme 1 hasn't been changed and enzyme 6 hasn't been changed, so everything else on here is going to remain about the same. Okay, yes, question.
Is there any possibility for you to give, for example, negative?
Yeah, negative feedback is actually the example, and maybe I forgot to talk about it. Negative feedback is actually the example they give right here. The way negative feedback would work in this example here on the notes is that the very end product actually inhibits enzyme 1, and by inhibiting enzyme 1, everything after that shuts off. So it decreases the amount of B made, decreases C, D, E, and therefore decreases F. What negative feedback is if the end product inhibits something at the beginning that causes less of that product to be made. That is, you're decreasing the amount of the end product being made. In contrast with that, with our example here, this was positive feedback because what G ended up doing was shutting off this top pathway, and we found out that the amount of G actually increased. That is an example of positive feedback. The existence of the product G itself actually increases the amount of G being made. Okay. Other questions on feedback? All right. So what happens? How will the answers about change if instead product G inhibits enzyme 1? Okay, so let's see. Product G inhibits enzyme 1. Tell me what's going to happen to B, C, D, F, and G. They will all decrease because you're inhibiting now the upstream part. You're inhibiting this thing, so everything after, it doesn't matter top or bottom branch, will decrease because you are preventing the production of product B. Yes?
Would there be more A then?
That's the next part here is, well, then what would happen to A? Well, if it's no longer being used, A is actually going to increase. It's going to build up because it's not being used. And therefore, you can make what conclusion about Z then? It's also going to increase. You've built a dam now in this river so that nothing can pass through enzyme 1. So everything starts building up. They do start increasing. Yes?
Why would Z increase?
Everything flows back. Is that I guess I should state this. Think of it as a river. Is that yes, it can continuously be made, but eventually enzyme 6 is not going to be able to make any more product because there's already plenty of product floating around, so Z should increase as well. Most likely, though, instead what this question will be phrased as is what happens to the activities of enzyme 1 and enzyme 6. Well, enzyme 1 is going to be decreased. Enzyme 6 will actually remain the same because it hasn't been affected. It's doing, it doesn't know that anything has changed. All it's doing is producing A, and A is going to fill up. Z is going to fill up too, but enzyme 6 doesn't know. It's going to keep trying to make more of product A. Let's see if there's anything else here. Usually this is presented, well actually, definitely, this is presented as a multiple choice question. Yes?
What happened to C, D, they all choose?
Yes, C, D, F, and G, and B. Basically everything after enzyme 1 will decrease because you're inhibiting enzyme 1. And again, for those listening on the video, we're answering the second part. Question here is how will all your answers that you made above change if product G instead inhibits enzyme 1? Okay. Let's see. Oh yeah, so all of this, I'm not going to go over because I lectured on it, but basically all of this here is to help you study and internalize what allosteric regulation means, which is this shift between active and inactive. I'll leave that to you guys, and you can watch the video on how to answer all that stuff. And then all these questions down here will help you internalize glycogen phosphorylase. If glycogen phosphorylase is not your extra credit question, it can still be separated into multiple choice questions, into several multiple choice questions. So you do still need to know it for the exam. And I will go down through that. And that's it for chapter 15 for now. We're going to end a little bit early because I didn't make a chapter 7 worksheet. So we will continue next week. And I know we're running out of time, but I'll pick it up and everything will be recorded on video. And I will do more stuff at the exam review next Wednesday as well. Yes?
Wednesday's recording?
Yes. Again, YouTube just takes a couple days to update these things.
Quick question.